Okay, hi group. We're looking today at quantitative analysis. We're just going to start chapter 5, and chapter 5 is going to extend our work with the mole. We're going to be looking at how to determine uh, amounts of reactants and products. So we've introduced stoichiometry as a definition in chapter 4, and stoichiometry is very quantitative. So the first thing we want to appreciate with this section is what exactly quantitative analysis is. So you have this worksheet here and you'll be filling in some information on it. Just want to start by showing you a graph that a chemist could use if you started out with a reactant, sodium carbonate, and that's your known mass, and then you add, according to this chemical reaction up here, an excess of calcium chloride to completely consume all of the sodium carbonate and precipitate as much of the carbonate as calcium carbonate. And then the calcium carbonate mass would be recorded. And this standard curve shows a very linear relationship between the mass of those reactants and those products. In this case, the calcium chloride would be what's called the excess reagent. We're going to see that definition in the note. The sodium carbonate would be the limiting reagent, might be the substance that we are trying to determine concentration for or an exact mass for. Maybe we don't actually know the mass of sodium carbonate. However, with linear relations, we can determine an equation for this line. And if we know, let's suppose we ended up with 1.5 grams of calcium carbonate. According to this linear relationship, we know what mass of sodium carbonate we started with. It would be about 1.6 grams. So it's a very exact relationship that is known, and this is what quantitative analysis is all about, is identifying the exact amount or measurement, usually as a mass of a substance. How is it that we can determine this mass relationship? Well, the information lies in the ratios of units that are reacting. In this particular reaction, sodium carbonate reacts 1:1 with calcium chloride. In the formula units follow that 1:1 ratio for those two ionic compounds. It's a balanced chemical equation, so we can make that comparison. That ratio is a ratio of units. It's not a mass ratio. We're not saying 1 gram reacts with 1 gram. We're saying that 1 mole of sodium carbonate requires 1 mole of calcium chloride to completely react. Usually when we do a reaction like this, we would be adding more than the required amount because we want to make sure that all of the sodium carbonate is used up. Okay, and whatever is present there, that will determine how much calcium carbonate we get, because there's also a relationship between those two compounds. They are also related in a 1:1 ratio by units, meaning that 1 mole of sodium carbonate can only produce 1 mole of calcium carbonate. We also have knowledge at this point of the relationship between moles and mass, and we do know that there is a link connecting moles and mass. So we have ways of determining for given reactants and products just exactly how much mass is required potentially, or how much mass is produced in a chemical reaction. So going back to our note here, that's the first definition which you want to add to your handout. The second one is looking at this general reaction equation. There is what's called a mole ratio. All right, the mole ratio is, as it sounds, it's just a comparison of the number of moles of any two chemicals in the reaction. We've already used this when, for the 3U students, you would be familiar with mole ratio already, because in the determination of a chemical formula, we needed to compare the number of moles of 2 or more elements in a compound in order to come up with the empirical formula. And so this mole ratio for all of our students now is something we need to understand. It's a comparison of not mass, but the number of moles of, for example, A to B, maybe A to C, or maybe B to C. There'd be 3 possible mole ratios in this reaction. Let's look at an example of a chemical reaction, and let's see if we can determine what the mole ratio is there.
In the reaction of a single P4 molecule with 6 Cl2 molecules, 4 molecules of PCl3 are produced.
Okay, so here's our result, is PCl3, and this is a little bit of a different chemical reaction because we're told that we start out with this P4 molecule. Okay, so that's some form of phosphorus as an element. Um, Now, previously we've looked at diatomic molecules. We've seen that we have Hofbrinkel as a way of remembering a lot of the diatomics. We also have some that are um, octahedral. We've seen sulfur. Now, phosphorus apparently can form molecules as 4 atom groups, and we're combining that with chlorine gas. So the reaction equation would be as a skeleton reaction equation as follows, and then we know that the product was 4PCl3. We saw the rearrangement of atoms. So the mole ratio here would be how many molecules of P4, which are just one to start with, and there were 6 Cl2 molecules, and then as a result 4PCl3 molecules are produced. The mole ratios are just the ratios of those coefficients. So we have moles of P4 to moles of Cl2 would be 1 to 6. We have moles of P4 to moles of the product PCl3 is 1 to 4. And then our last mole ratio, moles of chlorine gas to moles of phosphorus trichloride, would be 3 to 2 or 6 to 4. Okay, so those are mole ratios. We're just looking at the ratio of units on an atomic level. It would be ratios of molecules. On a molar scale, it's the ratio of how many molar units we have. Okay, let's move on. 2 more definitions that we need to add to this topic of quantitative analysis. I've mentioned already limiting reagent and excess reagent. Limiting reagent is probably the easiest one to start with because the term suggests that this reactant limits or controls the amount of product, and it's going to be the one that's present in the exact mole ratio, no more, no less, and it's going to be entirely used up. So it will be gone at the end of the reaction, and it will, because of that, it will limit how much product is formed. The excess reagent, usually a good rule to work with for excess reagent is you want to have at least 10% excess. In order to ensure that the limiting reagent is entirely consumed, we want to have at least 10% more than what we actually need for the excess reagent. Okay, now that doesn't sound like a lot, but when a mole is Avogadro's number of particles, if we have 10% more of, let's say, B, we have 10% times potentially Avogadro's number of particles if it was a 1-to-1. And that's a lot of extra. 10% of that is on the order of 10 to the 22, which is still huge. Okay, and that's going to make sure that all of the atoms or molecules of B can find all the atoms or molecules of A, and at the end, A is all used up, all gone, and B will be left over a little bit. The vinegar and baking soda reaction, we've seen that before, and this video here just reminds you that in a particular chemical reaction with only 2 reactants, one can be the limiting reagent, the other one can be excess, and we can visually see the evidence of that in this little clip.
In this reaction of baking soda and vinegar, the vinegar is the limiting reactant. We can use stoichiometry to predict the quantities needed for a complete reaction. We can predict the outcome of the reaction by precisely measuring the quantities of the reactants.
Okay, and that clip, which run a little long there, but the important part is at the very end, you're just adding heaps and heaps of baking soda. You're not really measuring how much of the excess reagent you're adding. You just want to make sure you have at least 10% so that you entirely use up all of the vinegar. And you see the reaction just ceases at some point. You're not getting any more carbon dioxide produced because the vinegar has been all used up, and all you're really doing is you're adding more baking soda to probably what would be a salt solution in water. I'm going to return to the standard curve method of quantitative analysis where we have a graph that relates a mass of product to a mass of reactant. And here we can use interpolation on the graph to determine the amount of a reactant, even though we don't know how much reactant we're starting with. But we can precisely and accurately measure to the best of our abilities using the best equipment that's possible some product mass. In this case, this reaction is a double displacement which forms a precipitate, and the lead to iodide, which is the solid product here, is going to be the component of the products that we can actually measure. The potassium nitrate is soluble, and the only way we would be able to determine its mass would be to filter the solid and separate it from the liquid, and then evaporate all the water from the aqueous potassium nitrate to determine its mass. But we have the compound lead to iodide in a filter paper. In this particular case, the method is kind of shown at the top. Suppose a volume of this excess reagent, which in this case would be our potassium iodide. We have at least 10% more than what we need, based on a 1 unit of lead to nitrate to 2 units of lead iodide, or sorry, potassium iodide. And this is going to completely consume a known amount of a limiting reagent. Now we say it's known, but really all we know about it is probably the volume that we are starting with. We don't know the mass that's present. So lead 2 nitrate will be all used up, and the maximum amount of product will be formed as a result using this 10% excess. The precipitate, which is our lead 2 iodide, is filtered and then separated from the solution, and then it's masked. So the standard curve is prepared using lots of different starting amounts. So you would prepare this reference data where you knew the mass of lead to nitrate to begin with, and you use values ranging from 1 to 5, and you carry out experiments where you measure the mass of precipitate that is obtained as a result, and then you have all of these relationships which you can graph. And you can prepare a standard curve where you're plotting how much lead to iodide is produced for a given amount of lead to nitrate. And then you can carry out analysis on an unknown sample that you know contains lead to nitrate. So you get your sample in your lab, you choose a chemical reaction which produces a precipitate, and you add your excess, and you measure the mass of lead iodide, and suppose you measure it to be about 3.6 grams, and you say, okay, well, knowing that this relationship is linear, I can interpolate on my graph and read back to the x-axis, which is representing the mass of the limiting reagent, and I can conclude that about 5 grams of the lead 2 nitrate must have been present in that solution. And then from there, if I wanted, I could determine maybe a concentration of that if I had measured its volume. Let's keep going with this example here. And I'm going to go and look at how to determine which chemical is the limiting reagent and which is the excess. So we're going to use mole ratio between reactants and products. We have to have a balanced chemical equation, so I'll use the same one that we've already introduced with the standard curve. And let's just state the mole ratio right up front. It's 1 to 2 to 1 to 2. So that's a balanced chemical reaction. And in this case, we have some scenarios here. So what if we started out with not 1 mole to 2 moles, but we knew that we had 0.2 moles of lead to nitrate and 0.6 moles of potassium iodide. So the required ratio is 1 to 2. The actual ratio in the reaction is 0.2 to 0.6, which is 1 to 3. So that means, and you can probably reason this out, that we have more than enough potassium iodide uh, that's required to completely use up the zero 0.2 moles of lead 2 nitrate. And so the potassium iodide will be the excess reagent and the lead 2 nitrate will be limiting. So this is the reasoning that you would come up with. Those are the conclusions. And let's look at the first explanation. So in reaction number 1, the reaction ratio, or reactant ratio, the actual, is 1 to 3. The required ratio is only 1 to 2. So we have more than what's necessary. That makes the limiting reagent the lead 2 nitrate, and the potassium iodide is the excess. So you can fill that in on your handout here where you have information missing. You can be filling in the items that we just went through. The second scenario here is looking at reaction possibility number 2, where let's say we have a half a mole of lead 2 nitrate and only 3/4 of a mole of potassium iodide. In that case, we can work it the other way. A 2 to 1 ratio demands that if we have a certain amount of potassium iodide, we need exactly half of that amount of lead 2 nitrate. Well, if we take 0.75 and we take half of that, half of 0.75 is less than 0.5, which means we have enough lead 2 nitrate and then a little bit more. Okay? We could reason it the other way and say a half mole of lead 2 nitrate would require double of the potassium iodide, so we really need 1.0 moles of potassium iodide. We don't have that, so it's going to limit the reaction. Okay, going the other way, we look at half of this is required, and we have that and more. Okay, so either way you reason it out when you explain your limiting and excess, it comes down to a mole ratio of what's required and what is actually present. So here's the explanation that I came up with. So you can record that information in your handout. At this point, that's enough to get you started. Take care.